Hi. So we have this chapter, quadratic functions. Uh, Quadratic functions are those functions, those polynomial functions whose maximum degree is 2, which means whose maximum power of the variable is 2. For example, x is square. The power of the variable x, the independent variable that is, x is the independent variable and y is the dependent variable. And that's your function, y equal to x square. So the power of the independent variable is 2, maximum power is 2, that's a quadratic function. So in general, any function of the form ax squared plus bx plus c would be a quadratic function. Here we have shown y equal to x squared. As you can see, the points 0, 0, 1, 1, 2, 4, minus 1, comma 1, minus 2, comma 4 are on the graph because all these points obey this function rule. And you can see that the shape of this is a bowl shape. In fact, all of the quadratic functions of the form ax squared plus bx plus c are somewhat similar to this. Similar kind of shape. It could be a bit narrower or much more wide than this, but it has the same bowl shape. It could also be inverted. Inverted bowl shapes are also quadratic functions. Sketches of different quadratic functions for different values of a, b, and c. Also note that a must not be equal to c. Because if a is equal to 0, this term goes away, and this is no longer a function whose maximum degree is 2. This then becomes a linear function. So we don't want to do that. We want to have a quadratic function. Quadratic function will not have a equal to c. Okay. So what are the different characteristics then of a quadratic function? The typical characteristics that we are looking for in any function are its domain and range, the x-intercepts, the y-intercepts, the y-intercept and not intercepts because there can only be one y-intercept for any function, while the x-intercepts could be multiple x-intercepts. So what's the domain of such a function? All values of x. Okay. So that's because any value of x is okay. There's no problem you put any value of x here, right? There's no square root in the definition. There's no denominator. It's not a function of the type 1 by x. It's just a polynomial function whose domain is all values, which is all real numbers. The range, however, is not all real numbers. Because as we saw, the x square function was sketched like this. And the x square function did not have any negative function values, any negative y values. They were not there. So the y values are all greater than equal to 0. So range was greater than equal to 0 in this case for y equal to x square. But for different quadratic functions, the range keeps changing. For example, this one, the range is greater than this number here, whatever this number is, -3. So y will be greater than equal to x. If it's an inverted function, whose maximum value is 1.5, the range of this is going to be y less than equal to 1.5. So different quadratics will have different ranges, but the range is never all real. It's a limited range. That's what I see. The x-intercept, as you can see, there are sometimes two x-intercepts, like in the green and the black function case, but sometimes only one x-intercept, like in the red function case. And sometimes there is no x-intercepts, like in this case, no x-intercept. So that is something to be investigated later on. How many and what are the x-intercepts? We'll come to that later on. The y-intercept would mean that the x value would mean that the x value is 0 because the y-intercept is somewhere on the y-axis, right? Like this one, the y-intercept of this green function is here. This is 0, comma, some number. That's the y-intercept. So that means I have to plug in x equal to 0 to get the y-intercept. If you plug in x equal to 0, what do you get? You get c. So the y-intercept is always c. If you are given y equal the function equal to ax squared plus bx plus c, the y-intercept is 0, comma c. That's always the case. Okay, so that was some introduction to quadratic functions, how they appear in shape, and some of their characteristics. Thank you.